Hello, this is the second part of Kirchhoff's law where we will learn about Kirchhoff's voltage law. So it's no brainer, unlike Kirchhoff's current law where we had dealt with currents, Kirchhoff's voltage law is all about voltages. So according to Kirchhoff's voltage law, the voltage around the loop equals to the sum of every voltage drop in the same loop for any closed network and also equals to 0. Put differently, the algebraic sum of every voltage in the loop has to be equal to 0, and this property of Kirchhoff's law is called as conservation of energy. Do you remember about loops from the previous course? So loops can be seen as the direction of the current flow. It doesn't really matter the direction of the loop because at the end you will get the same result as if the loop is pointing to the opposite direction. So when you begin at any point of the loop and continue in the same direction, note the voltage drops in all the direction, either negative or positive, and return to the same point. It is essential to maintain the direction either counterclockwise or clockwise, else the final voltage value will not be equal to 0. And that's a problem, because if the sum of voltage drops in a closed loop is different than 0, it means that you made some mistake somewhere in the equation. Just as this image shows here, the sum of voltage drops across each resistor has to be equal to 0. So let's do some exercises in order to understand this Kirchhoff's second law better. So we have this circuit here, and we have to find out the voltage drop across this particular resistor. The other voltage drops is already known, so the voltage drop across the battery is 1.51. Across this resistance is minus 0.55 volts, and across this resistance is minus 0.33. The first step is to choose the direction of the loop, which can be either clockwise or counterclockwise, right? Since I already solved this exercise, I have chosen to be clockwise, but it doesn't really matter which direction is. It's only important to stick with that direction once you decide which one to be. So we have 4 voltage drops, and the sum of each voltage drop must be equal to 0, right? Since the direction of the loop is clockwise, let's start replacing the value of these voltage drops in order, starting from the battery and coming back to the starting place. So 1.51 minus 0.55 minus 0.33 minus the voltage drop across this resistor will be equal to 0. And from this equation, it's really easy to find the unknown variable, and the final result is minus 0.63 volts. And that's it. This is how we managed to find out the voltage drop across this resistor. So easy, right? Now let's do another exercise. So we have this circuit here, and we have to find out the voltage drop across the battery. Basically, we have to find out the output voltage of the battery, and for the sake of exercise, let's pretend that the output voltage of the battery is not known, because in real world the voltage of the battery is written on the battery itself, right? So the first step should be to decide the direction of the loop, and let's stick with counterclockwise this time as well. Since we know the current flowing in the circuit and also the resistances of each resistor, we can find out the voltage drop across each component except for the battery. So voltage is equal to current times resistance. So 0.194 milliamps times 5 kilo ohms is equal to 0.97 volts. 0.194 milliamps times 20 kilo ohms is 3.88 volts, and so on. But wait a little bit. Why are these values negative? Well, the reason why these values are negative is because we have chosen a clockwise direction, and the battery's positive lead is here, and we know that electrons flow from positive to negative, right? And since the electrons flow counterclockwise and our loop is clockwise, we have to put a negative sign before each value. So again, the electrons start flowing from here, right? And if they flow from this direction, you have to put the voltmeter's positive red probe here and the black one here. Otherwise, if you switch them, your voltmeter will show you the same voltage drop, but with negative sign. Probably this sounds all complicated, but it isn't. And just as a tip, if you have circuits like this with a battery, try to choose the direction of the loop in the same direction with the electrons flow. In this case, counterclockwise, and therefore all these values will be positive, and the voltage drop across the battery will be negative. I hope it makes sense. If not, feel free to ask me any question below. So again, the sum of voltage drops in a closed loop circuit must be equal to 0, right? And the direction of the loop is clockwise, so this voltage plus this one plus this one and plus this one is equal to 0. Since all these three voltages are negative, and we are interested in the voltage drop of the battery, we can write down the following equation. And if we replace the values, we will get a voltage of 6.014 volts. Alright, so let's do another exercise. We have this circuit here, and we have to find the resistance of this resistor. So how can we do that? We have a closed loop here. Actually we have two, but let's first start with this one and see what happens. So we have chosen a clockwise direction, and so we can write down that 9 volts minus the voltage across this resistor minus 3.4 volts is equal to 0. And from this equation, we get a voltage drop of 5.6 volts. If we know the voltage across this resistor and the current flowing in this path, we can find out the resistance very easily using Ohm's law, right? So Ohm's law states that the voltage is equal to current times resistance, and from this resistance is equal to voltage divided by current. And now if we replace the values for the voltage and current, we get a resistance of 11 kilo ohm. Alright, this is the end of the course. Thanks for watching and see you next course.